Hello, this is Dr. Flight, and we're going to spend a little bit of time just with an introduction to multiple analysis of variance, MANOVA. Again, this is just an introduction to the concept of MANOVA. It will not have a deep amount of technical detail, but generally speaking, what MANOVA is about and when it may be appropriate to use MANOVA. So first, though, let's spend just a couple minutes reviewing ANOVA, because MANOVA is an extension of ANOVA, which would be an analysis of variance when we want to compare, if you will, two different groups, two independent groups, and determine whether they are different from each other based on some variable, and whether that variable is something that each group would respond differently to. So ANOVA then is a method where there's a dependent variable, and it's compared in a couple ways between two or more different groups. If we're looking at the mean of say satisfaction for one market segment, and we want to compare it to the mean score of satisfaction to a second market segment, the comparison of those two means is something that we would do, and we would want to identify whether and test the significance of whether there is a mean difference between those two groups, and then move on from there. So here's another example. If we use sales across three different groups, and we had one group that was exposed to an ad, we have ad A. We have a second group that was exposed to another advertisement, ad B. And then 3, we have a group that was exposed to no ad. Then what we would want to do is test to see whether the people responded differently, whether they saw group A or ad A, ad B, or no ad at all to sales in this particular case. So the treatment is what we call the ad exposure here. And the prediction that we would make, the null hypothesis, would be that there's no difference in sales between these three groups. That's ultimately what we would want to do. And so traditionally, we would run what we call a t-test to determine whether the mean across each of these three populations was in fact different or the same. So if we put this in some graphical terms, I'll pull up a few different things here. If a researcher wants to test the mean difference between groups, then in this case, we would look at 3 different exposures or 3 different tests, if you will, where we have one test, we have no ad versus ad A. So we would test the mean level of the group that did not see any ad to the mean level of the group that saw the mean of the group that saw ad A. And we would look at the difference between here. And so what we're going to say is maybe sales among the group that saw no ad were 15,000. Sales among the group that saw ad A might have been 20,000, and we'd look at the difference between these two groups, and we would do a statistical test and see if that difference is statistically different. So that would be one t-test that we would do. Second t-test that we might do is we might do no ad versus ad B in this case. Sorry, that should be a B. All right, that should be a B right there. So we look at this one and no ad, and in this case B looks like it's closer to 30,000 in terms of the number of sales that take place in that for the group that saw that ad. And then we'd be comparing this 30,000 to the 10,000-ish or 15,000-ish that was for no ad, the no ad group, and we do a t-test and compare those two means. Finally, we do a third test, and we'd compare A and B, and we would look at the difference between those. So if the researcher wants to simply know if collectively there's any difference across all three groups, then we run what's called an ANOVA, and the ANOVA would test whether the mean of no ad was equal to the mean of ad A, which was equal to the mean of ad B. And so that would be the F statistic that we would look at in ANOVA, and then we would test that. Again, univariate tests or independent t-tests dive a little bit deeper than the broader F statistic ANOVA, where we're running individual t-tests tell us what's going on underneath the surface. Sometimes we run these as an ANOVA with a post hoc test. So we might run a Chefé or a Touquet or a Bonferroni post hoc test while we do an ANOVA. And when we do that, we're in essence running these individual t-tests, all in one collection. So in this example, it appears that advertisement treatment has an effect on sales because we had no ad, then we had A, and then we had B. It would seem as though ad B is more effective than ad A, but both ad A and B are more effective than no ad at all. Again, the test would help us do that. So this is a basic ANOVA. Now, once we start moving into MANOVA, then what we may have here are multiple dependent variables. So in this illustration, we continue to have a situation where we have our advertisement treatments, but now we're going to add something else, word of mouth, in addition to sales, and we're going to look at multiple dependent, so these are dependent variables. So these are our DVs in the model, if you were going to look at those. And then these down below, the treatments or the groupings would be, this one variable here would be an independent variable. So that's what that would be classified as. And so we'll pull up some more information here and pull up everything that we have so you can kind of see. We have our original X's indicated on the graph for sales where they were in the previous slide, but now we've added the little star to indicate word of mouth. And it would appear again that we have a different, we have a new variable, word of mouth, but it looks like there's a significant difference, or that there's a difference anyways, between word of mouth. Now this is on a different scale. This is a 1, 5, 10 scale, but it would appear as that though the no ad would be somewhere around a 0 or a 1, somewhere maybe a little below 1 perhaps. And then the ad A word of mouth is somewhere up here, maybe around 7 or 8. And then the ad B word of mouth would be somewhere maybe around 6. So in this case, we have maybe a 1, an 8, and or 7.5 maybe, and a 6. So it certainly looks like no ad versus ad A and B. It looks like there's a significant difference there. Now we don't know whether there's a difference between a statistical difference between word of mouth for ad A or ad B, but that we could obviously test that. So, and this is also a little bit different because, we saw that sales increased with each of the different ad treatments, but word of mouth doesn't necessarily increase between ad treatments. In fact, B is lower than A, even though we got more sales out of B. So it might be that A might be a very memorable ad that people want to talk about, but it may not be necessarily effective in driving sales when compared to ad B. If you want to create more buzz, then that might be the ad to run. But ad B may have something in it that might have a more compelling message, but it may be a little less memorable, or it may be less something people are talking about. So that's why its word of mouth might be a little bit low. But a MANOVA, though, allows the examination for and identifies a difference between several dependent variables. And in this case, again, word of mouth and sales. And this may be across one or more non-metric independent variables. In this case, we have add treatment, which is a single independent variable. We could have multiple independent variables if we wanted to, as far as the model goes. So MANOVA then extends ANOVA because you can add dependent variables, our DVs here, and you can also add independent variables and look at the interaction between those if an interaction exists. So that's kind of where the power kind of comes in here of a MANOVA, being able to simultaneously look at multiple IVs and DVs, whereas ANOVA only allows you to have one treatment, like advertisement treatment, and typically one dependent variable at a time. So ANOVA then creates a linear combination or variate of the dependent variable for each level, or this should say MANOVA. I don't know why I have that. Sorry about that. MANOVA creates a linear combination of a variate for each dependent variable that's created. So if we look at this in a little bit more context, I know there's quite a bit on this page, but we'll just kind of walk through here. Remember our original example is this one. This is like what we had in the MANOVA, this is what we just had in the MANOVA, excuse me, with sales and word of mouth. And we have this weight then that will be assigned to sales and to word of mouth. And there will be a composite variable or a linear combination of these two, which will be kind of like a score that could be assigned to each of the different levels that we have. So again, we have this down below. We're going to look at these down below, where we have a C for the individuals who had no add, a C for the individuals who saw add A, and a C for the ones who were exposed to add B. So these are our add treatments: no add, add A, and add B. Our dependent variables, we have two. We have sales and we have word of mouth. So again, just working off our terminology, the add treatment is our independent variable in this case. Dependent variables in this case, in terms of the way we describe this, are sales and word of mouth. And then this C is like a composite variable. It's a combination, linear combination in this case, of the variate of the W1 and W2, and that's where we go. Now, jumping back up here, traditionally when we do this, what we're saying is that the null hypothesis, if we're going to do some testing here, is that each of the C's would be equal to each other. So each of the linear combinations in this case would be equal to each other. So this is a little extension of ANOVA, because before we would have said it was simply the mean of one variable, the one dependent variable for each of the three treatments. Now we're saying it's the composite value of the variate that's going to be equal to all three. So for this here, this would be the test. And the basic test, again, for an ANOVA, if we do an F test, and then extending it here with be a MANOVA, would be that all of these relationships exist. C no add equals C add A equals C add B, and then by default, we would know that C add B equals C A no add. So, we kind of, get all three relationships identified here, and that each hold in order for this hypothesis to be true. So that's kind of the way this extension more or less works as we think about this. And we want to know what kind of MANOVA is. So MANOVA then, in a kind of a recapitulation here, it is a linear combination of the dependent variables, and for each level of independent variable that we have. You'll know and you'll read as you look at this a little bit further that MANOVA and discriminant analysis might be similar to each other, or they might look similar to each other in the way the variates are created and how they look. But what's different here is that the independent variable, in this case ad exposure, is now also the grouping variable. And so it flip-flops a little bit. We're not really used to seeing the independent variable be a metric, be non-metric, and be the grouping variable. What we're used to doing is seeing that be the dependent variable. Like we're trying to identify groups in this particular case. And this is a little bit different because we know groups and we know what's there. What we want to do is identify differentiating dependent variables. And so the dependent variable, the DV, is going to be metric. And so that's a little bit backwards and a little bit different from what you would most normally think about. So the variant then that ultimately gets created, again, we saw it already, but we got this composite variable. So this should actually be a composite here, not so much a constant, or a linear combination of a weight plus the x then that's associated with the first variable. So it might dependent variable, so it might be word of mouth, and then it might be sales and so on. So each respondent then has one of these scores calculated for them, and the weight that's estimated is used by MANOVA to create this calculation that we have. Okay, so just continuing on then, again, I'll emphasize this idea that most people are used to the term dependent variable in a regression as the variable that's observed and influenced by independent variables. Oftentimes when we do a typical regression, we see the dependent variable on the left side of the formula and the independent variables on the right side of the formula. And the other thing is, and the way you think about this, is that the independent variables are typically the ones that are manipulated, and the dependent variables are the ones that we observe a difference in. So think about our grouping variable as the one that we're creating or manipulating change in. So like in an experiment, we had add A, add B, and then we had no add. In an experiment, we created that scenario by which we had this distinction, and now we want to see the observed change in the dependent variables, which in this case are happen to be the metric variables, word of mouth and sales. So it's flip-flopped, as I mentioned before. MANOVA is not a regression. And again, the terminology will certainly seem as though it's flipped around. Keep in mind there are some other idiosyncrasies that in a MANOVA we need there must be two or more dependent metric variables. If we don't have two or more, then it would be an ANOVA in that particular case. There don't have to be more than two or more than one independent or non-metric variables. So in this case, all we had was add treatment, but we could add another non-metric variable. We could have like add treatment, which had 3 levels. And then on top of that, we could say like customer longevity, whether the customer is a long-standing customer of ours or not, something along those lines. And then the variate, of course, is formed on a set of dependent variables. So again, in this last case, we saw how the weight, the W, was assigned or in relation to the X values. In this case, the X values are our dependent variables, and it was word of mouth and it was sales. Okay, so So that's going to be just something to keep in mind in structuring your data and trying to understand how it looks and how you're going to actually apply this method in practice when you have a data set. You need to make sure that you're using the right type of data as a dependent variable versus an independent variable, and that it's going to be swapped around from what you would typically think. So in this instruction, and as we walk through this material, the term independent variable will indicate the grouping variable then, and it'll reinforce the notion that the independent variable is non-metric and it contains the testing levels, and it's what we would change in an experiment to identify a change in what we would think is a causal variable that is the dependent variable. Again, extending this idea just to say that we can have more independent variables. In this case, if we look at the inner middle here, we have sales and we have word of mouth. So those are our two dependent variables we had before. However, now we have not only ad treatment, so we have ad treatment with no ad, ad A, and ad B, but what we also included was a second independent variable called distribution. And in this case, we have magazine and we have newspaper. So we could put an ad A in a magazine, or we could put it in a newspaper, or ad B in one or the other. This might be a little bit of a, I don't know how we would do this, have no ad in one or the other. I suppose what we could do is just let people look at a magazine or look at the newspaper with no ad in it, so that they would look, but they wouldn't see the ad at all. And so now what we can do is we can look and see the distinction between levels in ad treatment, but then we can also look at distinctions and differences in sales and word of mouth across magazine and newspaper, and then the interaction between them as well. So if we have a magazine with ad A and a magazine in ad B, we can look at the differences between those in sales and word of mouth. So there's an interaction that's happening as well between the two treatments that we're doing, so the distribution treatment and the advertising treatment. Please note that the total number of groups that we have is going to be 6. It'll be the number of treatments for each multiplying the two treatment levels, 2 and 3, 2 distribution, 3 ad, we give our 6, and that's how many we have. So when we execute this, when we actually run this analysis, we need to make sure that we have a large enough sample size in each cell to be able to run the analysis and move forward with it. So we want to make sure we have enough power, in other words, to be able to do this. So that's the extension then of ANOVA, to be able to accommodate more than one dependent variable and then be able to handle more than one independent variable simultaneously while measuring the interactions between the two. And again, this is something that discriminant analysis would not allow you to be able to do, and so it may be something we want to look forward to as we move forward. So just to wrap this up then, we want to do a MANOVA when we have several dependent variables as opposed to one. When running independent ANOVAs, is a key thing here is it doesn't allow for errors across the tests. So in other words, when we run individual t-tests, like in post hoc testing, then errors may happen, and between the two shared variance and error, and shared error can happen between the t-tests that don't get picked up but would get picked up in a MANOVA. So that could be an important thing to think about. Experimental design. So when we're unable to randomize the groups, then MANOVA may be more appropriate than ANOVA, and there may be some non-experimental design situations that are called quasi-experiments when randomization doesn't happen in the sampling situation or in the sampling plan. And so that might be a time when MANOVA is appropriate in a quasi-experiment when we're not able to control everything the way we would like. Okay, so this was just a brief kind of like soft introduction to MANOVA, and structurally just remember kind of what those cells look like in terms of setting up your experiment. Okay, all right, so look, if you have any questions, look forward to hearing from you, and please, yeah, just reach out if I can help. Thank you.